Close your eyes for just a moment. Imagine you're floating in the darkness of space, suspended in the velvet black between stars. You're watching a star, an ordinary star, massive and ancient, quietly burning through the last of its fuel. For millions of years, it has hung in the cosmic dark, a beacon of light and heat. And then, in an instant that defies comprehension, it begins to die. But this isn't a quiet death. This isn't a star simply fading away into the night. This is a death so violent, so powerful, that for a few brief moments, this single dying star will shine brighter than an entire galaxy of 100 billion suns. This is a supernova, and it is simultaneously the most destructive and most creative event in the universe. We call them supernovas, these spectacular deaths, and the name feels almost inadequate for what they truly are. They are cosmic phoenixes, stars that end their lives in blazing glory while simultaneously planting the seeds of future generations. They are the universe's way of recycling, of taking the old and transforming it into the new. They are the forges where the very atoms that make up your body were created, the calcium in your bones, the iron in your blood, the oxygen filling your lungs with each breath you take. Tonight, as you drift into sleep, let me take you on a journey through one of the cosmos's most profound mysteries. We're going to explore what happens when a star dies, not peacefully, but explosively. We're going to witness the moment when gravity wins its final battle, when a stellar core collapses in less than a second, when temperatures soar to billions of degrees, and when enough energy is released to outshine galaxies. We're going to understand the difference between the types of cosmic explosions that light up the universe, see how the remnants of these explosions seed new worlds, and discover why astronomers around the globe are watching certain stars right now, waiting for the next great supernova to appear in our skies. This isn't just about destruction. It's about the strange and beautiful truth that the most violent events in the cosmos are also acts of profound creation. Every supernova is a death, yes, but it's also a birth announcement for the next generation of stars, planets, and perhaps even life itself. So let yourself relax now. Take a deep breath. Let these cosmic questions wash over you like waves. There's no test at the end. No need to remember every detail, just allow yourself to wonder, to imagine, to feel the weight and beauty of these stellar deaths. Because in understanding supernovas, we understand something fundamental about our own existence. We understand that we are, quite literally, made of stars that died long before our sun was even born. Let's begin at the beginning, with the life that comes before the death. The life before death. Before we can understand how a star dies, we need to understand how it lives. And for massive stars, the ones that will one day explode as supernovas, life is spectacular but brief. Think of a star as a constant battle between two fundamental forces. On one side, you have gravity, always pulling inward, always trying to collapse the star down to a single point. On the other side, you have the energy of nuclear fusion in the star's core, creating heat and pressure that push outward, resisting gravity's crush. For most of a star's life, these two forces are in perfect balance. The star is stable, serene, a glowing sphere of plasma suspended in equilibrium. But this balance requires fuel, and that fuel is the star itself. When a massive star first ignites, somewhere between 8 and 100 times the mass of our Sun, it begins by fusing hydrogen into helium in its core. This is the same process that powers our own sun, and it's remarkably efficient. The star can burn hydrogen for millions of years, depending on its size. Our sun, for reference, will spend about 10 billion years in this phase. But massive stars, because they're so much bigger and burn so much hotter, race through this stage in just a few million years at most. Imagine that. A star that outweighs our sun by 50 times might live for only 5 million years. That sounds like a long time to us, but in cosmic terms, it's the blink of an eye. Dinosaurs roamed the Earth for longer than some massive stars exist. When the hydrogen in the core runs out, something remarkable happens. The core begins to contract under gravity's pull. This contraction heats the core up, and when it reaches about 100 million degrees, helium begins to fuse into carbon and oxygen. The star has entered a new phase of its life. But here's the thing. Helium fusion doesn't last as long as hydrogen fusion, not even close. A star might burn helium for only a few 100,000 years. And then the pattern repeats. The helium runs out. The core contracts again. The temperature rises, and now carbon begins to fuse, creating neon and magnesium. Then neon fuses, then oxygen, then silicon. Each time the fusion stage gets shorter. Carbon burning might last a few thousand years. Oxygen burning just a few years, silicon burning mere days. The star becomes like an onion, with different layers burning different fuels. At the very center, you have the core, growing denser and hotter with each fusion stage. Surrounding it are shells where lighter elements are still burning. There's a shell of silicon burning around the core, a shell of oxygen burning around that, then neon, then carbon, then helium, and finally, at the outermost edges, hydrogen still fusing away as if nothing has changed. But everything has changed, because the star is building toward a crisis. Each fusion reaction in the core produces heavier elements than the one before. Hydrogen fuses into helium, helium into carbon and oxygen, carbon into neon and magnesium, oxygen into silicon and sulfur, silicon into iron and nickel. And here, at iron, the chain stops. Iron is special. It's the most stable nucleus in the universe. Fusing iron into heavier elements doesn't release energy. It requires energy. Iron is a dead end. When the core finally becomes primarily iron and nickel, the star has reached the end of the road. There's no more fuel to burn, no more energy to generate, no more outward pressure to resist gravity's inward pull. The stellar core sits there, inert, a ball of iron about the size of Earth, but containing more mass than our entire sun. And it's only a matter of time before gravity wins. Let yourself feel the weight of this moment. For millions of years, this star has been fighting against its own gravity, burning fuel to stay inflated, to stay alive. But now the fuel is gone. The core is iron, and iron cannot save it. The star has perhaps hours left to live. The calm before the storm is almost over. The collapse is about to begin. Take a breath. Rest in this knowledge for a moment. Everything that comes next happens almost too fast to comprehend. But before we watch this star die, remember, this death is what makes our lives possible. Every atom of iron in your body, every bit of calcium and carbon and oxygen was forged in the core of a dying star billions of years ago. That star's death is why you're alive. Now let's watch what happens when a stellar core finally gives in to gravity. The moment of collapse. The collapse begins without warning. One moment, the iron core is stable, supported by electron degeneracy pressure, a quantum mechanical effect where electrons refuse to be squeezed too close together. The next moment, the core's mass crosses a critical threshold about 1.4 times the mass of our Sun. This is called the Chandrasekhar limit, named after the astrophysicist who calculated it. Beyond this mass, electron degeneracy pressure simply isn't enough anymore. And then gravity wins. What happens next is almost impossible to believe. The core, which has a radius of about 2,000 kilometers, roughly the size of a small planet, collapses down to a radius of about 50 kilometers in approximately 1/4 of a second. Read that again. 2,000 kilometers becomes 50 kilometers in 1/4 of a second. That's not a gentle settling. That's a catastrophic implosion happening faster than you can blink. The matter at the outer edge of the collapsing core accelerates inward at velocities approaching 23% of the speed of light. Think about that. Nothing in your everyday experience moves anywhere near that fast. Light travels at about 300,000 kilometers per second. This collapsing stellar material is moving at nearly 70,000 kilometers per second. At that speed, you could travel from Earth to the Moon in about 5 seconds. As the core collapses, the density and temperature skyrocket. Electrons are forced into protons, creating neutrons and releasing neutrinos in a process called electron capture. The electron fraction of the core, the proportion of electrons to other particles, drops from about 42 to 45% down to 30%. Billions upon billions of neutrinos stream outward from the core, carrying away energy but barely interacting with anything. They pass through the rest of the star as if it weren't even there. The temperature in the core reaches 100 billion degrees Kelvin. To put that in perspective, the core of our Sun is about 15 million degrees. This collapsing stellar core is more than 6,000 times hotter than the center of the Sun. At these temperatures, matter behaves in ways that seem almost alien. Nuclear reactions happen in microseconds. Photons have enough energy to create particle-antiparticle pairs out of nothing. The laws of physics that govern our comfortable everyday world are stretched to their absolute limits. And then, at nuclear saturation density, about 3 times 10 to the 14th grams per cubic centimeter, the collapse stops. Abruptly, the neutrons themselves, pressed together at nuclear density, resist further compression through another quantum mechanical effect called neutron degeneracy pressure. The collapsing core has become a proto-neutron star, a ball of incredibly dense matter about the size of a city, but containing more mass than our entire Sun. Here's where things get even more dramatic. The material that was falling inward at a significant fraction of the speed of light suddenly encounters this wall of neutron degeneracy pressure. It can't keep falling, so it bounces. Imagine dropping a ball onto a hard floor. The ball compresses slightly on impact, then springs back, bouncing upward. Something similar happens here, except the ball is the inner core of a dying star, and the floor is neutron degeneracy pressure, and the bounce creates a shockwave powerful enough to blow apart an entire star. This bounce launches a shockwave outward through the rest of the collapsing core. But here's the problem. The shockwave stalls. It doesn't have quite enough energy to push through all that infalling material. In computer simulations, this stalled shock is a major headache for astrophysicists. How does the explosion actually happen if the shock wave stalls just a few hundred kilometers from the center? The answer lies in neutrinos. Remember all those neutrinos being created in the core. They're streaming outward at the speed of light. And while most of them pass through matter without interacting, not all of them do. A tiny fraction, less than 1%, deposit their energy in the region behind the stalled shock wave. And because there are so many neutrinos, an almost unimaginable flood of them, that tiny fraction is enough. Over the course of a few tenths of a second, the region behind the stalled shock heats up from neutrino interactions. Turbulence develops, convection currents form, with hot material rising and cool material sinking, creating a roiling, chaotic zone. This turbulence helps neutrinos deposit even more energy. It's a feedback process, and it's assisted by something called the standing accretion shock instability, or SASI, which causes the stalled shock to oscillate and deform in non-spherical ways. Eventually, after what might be half a second to a second of this complex interplay between neutrinos, turbulence, and hydrodynamics, the shock is re-energized. It begins moving outward again, accelerating as it plows through the outer layers of the star. In the core, the proto-neutron star settles into its new existence. Over the next 10 seconds, it releases about 10 to the 46th joules of energy, mostly in the form of neutrinos. To give you a sense of scale, that's 100 times more energy than our Sun will produce over its entire 10 billion-year lifetime. Released in just 10 seconds of that enormous energy output, perhaps 1% goes into the kinetic energy of the explosion we see. The rest, 99%, streams away as neutrinos, invisible messengers of the star's death. If the proto-neutron star has a mass below about 20 solar masses worth of material falling back onto it, it will survive as a neutron star. These are among the strangest objects in the universe. A ball the size of a city, where a teaspoon of matter would weigh as much as a mountain, spinning at incredible speeds, with magnetic fields trillions of times stronger than Earth's. But if too much material falls back onto the proto-neutron star, if it ends up with more than about 2 to 3 solar masses, even neutron degeneracy pressure isn't enough. The neutron star collapses further, falling through its own event horizon, becoming a black hole. No explosion, no light, just a region of space-time so warped that not even light can escape. For stars more massive than about 40 to 50 solar masses, the collapse might be so extreme that they skip the supernova stage entirely, falling directly into a black hole without producing the spectacular explosion we call a supernova. These are called failed supernovas, and they're a reminder that even in the universe's most dramatic events, there can be different outcomes. But when the explosion succeeds, when that shockwave breaks through the outer layers and reaches the surface of the star, something magnificent happens. The star brightens. Spectacularly. It becomes a supernova. Let yourself rest with this image for a moment. In less than 1 second, a stellar core the size of a planet has collapsed to the size of a city. In that same second, enough energy has been released to rival the output of all the stars in a galaxy. A shockwave has been launched outward at tens of thousands of kilometers per second, and a new neutron star or black hole has been born. This is the moment of collapse. This is the instant where life becomes death, becomes something entirely new. And we're only at the beginning of understanding what this means. Now, let's talk about the sheer power unleashed when this shock wave reaches the star's surface and announces the death to the cosmos. The power of a single explosion. There's a moment right when the shock wave breaks through the stellar surface, when the dying star becomes something extraordinary. Astronomers call it the shock breakout, and it's one of the most powerful events in the universe. Imagine you've been watching this star, this red supergiant hanging in space. For years, perhaps centuries, it's been burning steadily, a constant point of light. And then, in the span of a few minutes, it suddenly brightens by a factor of thousands or even tens of thousands. The breakout is so intense, so sudden, that if you happen to be looking at the star through a telescope at the exact right moment, you might actually see it happen in real time. This initial flash lasts only minutes to hours, but it's a preview of what's coming. Over the next days and weeks, the supernova continues to brighten as the expanding debris becomes optically thin and more of the interior is revealed. The star reaches peak brightness, and at that moment, it can outshine its entire host galaxy. Let that sink in for a moment. One star, a single star among billions, becomes brighter than all the other stars combined. A typical galaxy contains 100 billion stars or more, and for a brief time, one dying star matches or exceeds the light output of all of them. The numbers involved are almost meaningless, they're so large. A typical core collapse supernova releases about 1 to 2 times 10 to the 51st ergs of kinetic energy in the explosion. In more familiar units, that's about 10 to the 44th joules, or if you prefer, about 2 trillion watts of power. Our entire Sun produces about 4 times 10 to the 26th watts. So a supernova at its peak is about 5 trillion times more powerful than our Sun. But even that doesn't fully capture the scale. The absolute magnitude of a Type II supernova at peak brightness is around -19.3. In observational astronomy, magnitude is a logarithmic scale where more negative numbers mean brighter objects. The Sun has an absolute magnitude of +4.8. Each 5 magnitudes of difference represents a factor of 100 in brightness. So a magnitude of -19.3 is about 5 billion times brighter than the Sun. If you placed a typical Type II supernova at the same distance as the Sun, it would completely overwhelm everything. You couldn't look at it. It would be far brighter than the Sun appears to us from Earth, bright enough to cause immediate eye damage. Of course, at that distance, the radiation and energy would also sterilize the entire inner solar system, but the brightness alone would be staggering. Some supernovas are even more extreme. In recent years, astronomers have discovered a class of explosions called superluminous supernovas that are 10 to 100 times brighter than typical supernovas. The record holder for a while was an object called ASASSN-15LH, discovered in 2015 by the All-Sky Automated Survey for Supernovae. ASASN-15LH, at its peak, was about 50 times more luminous than the entire Milky Way galaxy. Think about that. Our galaxy contains somewhere between 200 and 400 billion stars. All of them combined produce a certain amount of light. And this single exploding star, for a brief time, was 50 times brighter than all of those stars together. It had a bolometric luminosity of about 2 times 10 to the 45th ergs per second, nearly 1 trillion times brighter than our Sun. If ASASN-15LH had been in our galaxy at the distance of, say, Betelgeuse, which is a few hundred light-years away, it would have shone brighter than the full moon in our sky. According to one astronomer, if it were in our own galaxy, it would shine brighter than the full moon. There would be no night, and it would be easily seen during the day. Imagine that, a star so bright that it eliminates night entirely, casting strong shadows even at midnight. The extreme brightness of superluminous supernovas is still not fully understood, and astronomers continue to debate the mechanism. The leading theory proposes that they're powered by magnetars, rapidly spinning neutron stars with extraordinarily strong magnetic fields. As the magnetar spins down, losing rotational energy, it pumps energy into the expanding supernova debris, causing it to glow with exceptional brightness for an extended period. Other proposed explanations involve the collisions of previously ejected shells of material or the presence of enormous amounts of radioactive nickel-56 produced in the explosion. The true mechanism may vary between different events, and this remains an active area of research. But even a normal garden-variety supernova is a spectacle almost beyond comprehension. The expanding debris, ejected at speeds of 5,000 to 20,000 kilometers per second, or roughly 3 to 6% of the speed of light, carries the kinetic energy of the explosion outward into space. This isn't a gentle expansion. Material is moving so fast that if it could travel in a straight line, it would cross the distance from Earth to the Sun in about half an hour. The light we see comes from several sources. Initially, it's shock-heated material glowing from the sheer energy of the explosion. Later, as the debris expands and cools, the light is powered by radioactive decay. In particular, nickel-56 decays to cobalt-56 with a half-life of about 6 days, and then cobalt-56 decays to stable iron-56 with a half-life of about 77 days. These decay chains release gamma rays that heat the expanding gas, causing it to glow in visible light. The light curve of a supernova, the graph of brightness versus time, has a characteristic shape. It rises rapidly to peak brightness over a couple of weeks, then declines. For Type II supernovas, there's often a plateau phase where the brightness stays relatively constant for a few months before declining more steeply. This plateau happens when the expanding photosphere reaches the star's hydrogen envelope, and the recombination of hydrogen ions provides a steady source of opacity that maintains the luminosity. For an observer watching from a distant planet, a supernova is a transient event. Where once there was a star, suddenly there's a brilliant new light in the sky, brighter than anything except perhaps the moon and planets over weeks and months. This new star slowly fades, eventually disappearing from naked eye view. But for those weeks or months, it's a reminder of the incredible violence and power present in the cosmos. And here's something beautiful to contemplate as you let yourself relax. That power, that immense release of energy, is not destruction for its own sake. It has a purpose. The energy of the supernova explosion is what disperses the star's newly forged elements into space. Without that violent expulsion, all the carbon and oxygen and silicon and iron created in the star's core would simply collapse into the neutron star or black hole at the center, lost forever. The explosion is what returns those elements to the universe, making them available for the next generation of stars and planets. Take a deep breath. Let the scale of this settle in your mind. One star dying, releasing more energy in a few seconds than our sun will produce in its entire 10 billion-year lifetime, outshining billions of stars, visible across the universe, a beacon announcing death and rebirth simultaneously. But not all supernovas are created equal. There are different paths to this cosmic explosion, different types of stars that can end their lives in brilliant blazes. Let's explore the varieties of stellar death. 2 paths to cosmic fireworks. In the grand scheme of the cosmos, there are essentially two fundamentally different ways to make a supernova. The first, which we've been discussing, is the core collapse supernova. The second is the thermonuclear supernova. They look similar from a distance, both brief and brilliant explosions, but the underlying physics couldn't be more different. Core collapse supernovas, also called Type 2, Type 1b, and Type 1c supernovas, are the deaths of massive stars. These are stars that were born with at least 8 times the mass of our Sun, giants that lived fast and died young. We've already explored the mechanism. The iron core collapses, a shockwave forms, neutrinos deposit energy, turbulence helps revive the shock, and the star explodes. These explosions leave behind a neutron star or black hole at the center. The naming convention can be a bit confusing because it's based on spectroscopy rather than the physical mechanism. Type 2 supernovas show strong hydrogen lines in their spectra because the massive progenitor star still had its hydrogen envelope when it exploded. Type 1b supernovas lack hydrogen lines but show helium because the star had lost its hydrogen envelope, likely through stellar winds, before exploding. Type 1c supernovas lack both hydrogen and helium lines, indicating an even more stripped progenitor star, possibly a Wolf-Rayet star, that shed most of its outer layers before death. All three of these types share the same basic mechanism: core collapse of a massive star. The differences in their spectra just reflect differences in how much of the original stellar envelope was still present when the core finally gave out. But then there's Type 1a supernovas, and these are entirely different beasts. Type 1. A supernovas don't involve massive stars at all. Instead, they involve white dwarfs, the dense remnants left behind when Sun-like stars die. A white dwarf is what our Sun will become in about 5 billion years, a ball of carbon and oxygen about the size of Earth, but containing roughly the mass of the Sun, supported by electron degeneracy pressure, no longer undergoing fusion, just gradually cooling over billions of years. That's the fate of most stars in the universe. A quiet decline into a white dwarf, then a slow fade to darkness over timescales longer than the current age of the universe. But under certain circumstances, a white dwarf can explode. The key is the Chandrasekhar limit again, that critical mass of about 1.4 solar masses. A typical white dwarf has a mass of around 0.5 to 1 solar mass, safely below the limit. But if a white dwarf can somehow gain more mass, if it can approach that critical threshold, something remarkable happens. Most Type 1a scenarios involve binary star systems where a white dwarf is orbiting a companion star. If the two stars are close enough, the white dwarf's gravity can pull matter off the companion star in a process called accretion. This accreted material, usually hydrogen or helium, falls onto the white dwarf's surface, gradually increasing its mass. As the white dwarf's mass grows towards the Chandrasekhar limit, its interior pressure and temperature increase. Remember, the white dwarf is made primarily of carbon and oxygen, the products of helium fusion from the star's earlier life. Normally, these elements don't fuse because the temperature isn't high enough and there's no ongoing energy source. But as the mass increases and the center compresses, the core temperature rises. When the white dwarf reaches about 99% of the Chandrasekhar limit, something critical happens. The central temperature reaches about 700 million degrees and carbon fusion ignites. But unlike in a normal star, this fusion doesn't happen in a controlled way. In a normal star, if the core heats up from fusion, the star expands slightly, which cools the core, providing a natural thermostat. But a white dwarf is supported by electron degeneracy pressure, not thermal pressure. The outward pressure doesn't depend on temperature, so when carbon fusion begins and the core heats up, the white dwarf doesn't expand to cool things down. Instead, the higher temperature just makes the fusion happen faster, which releases more energy, which increases the temperature further, which accelerates the fusion even more. It's a runaway process, a thermonuclear explosion. Within seconds, a significant fraction of the white dwarf's carbon and oxygen undergoes fusion, creating an enormous amount of energy, 1 to 2 times 10 to the 44 joules. This energy is more than enough to completely unbind the white dwarf, to blow it apart entirely. Unlike a core collapse supernova, which leaves behind a neutron star or black hole, a Type 1. A supernova completely destroys the progenitor star. Nothing remains except the expanding debris. The fusion reactions in a Type 1a produce large amounts of nickel-56, which subsequently decays to cobalt-56 and then to iron-56, just like in core collapse supernovas. This radioactive decay powers the light curve, making Type 1a supernovas bright for weeks to months. There's a second possible scenario for Type 1a supernovas, the merger of 2 white dwarfs. If 2 white dwarfs orbit each other closely enough, they gradually lose orbital energy through gravitational wave radiation, a process predicted by Einstein's general relativity and now confirmed by observations. Over millions or billions of years, the orbit decays and eventually the 2 white dwarfs merge. If their combined mass exceeds the Chandrasekhar limit, the result can be a Type 1a supernova. Astronomers still debate which scenario is more common, the single degenerate model with accretion from a companion or the double degenerate model with 2 merging white dwarfs. It's possible both happen in nature, and the relative frequency might depend on the galaxy's age and star formation history. What makes Type 1a supernovas particularly interesting to astronomers is their remarkable uniformity. Because they all explode when a white dwarf reaches approximately the same mass, about 1.4 solar masses, they all release roughly the same amount of energy and reach approximately the same peak brightness. With some calibration based on the shape of their light curves, Type 1a supernovas can be used as standard candles to measure cosmic distances. This is no small thing. Measuring distances in astronomy is notoriously difficult, especially at large scales. But because we can determine the intrinsic brightness of a Type 1a supernova, and because we can measure its apparent brightness as seen from Earth, we can calculate how far away it must be using the inverse square law. This technique has been used to measure distances to galaxies billions of light-years away, and it was the key to discovering that the universe's expansion is accelerating, a finding that earned the 2011 Nobel Prize in Physics. So we have 2 paths to cosmic fireworks. On one hand, the core collapse supernovas, the deaths of massive stars, powered by gravitational energy and neutrinos, leaving behind exotic remnants. On the other hand, the thermonuclear supernovas, the violent disruption of white dwarfs powered by runaway fusion, leaving nothing behind but expanding debris. Both types contribute to the chemical enrichment of galaxies. Both types can be visible from billions of light-years away. Both types are crucial to our understanding of stellar evolution and cosmic history. And both types, in their own ways, are beautiful reminders of the universe's capacity for transformation. Let yourself rest with these images, a massive star collapsing inward, then exploding outward. A white dwarf pushed past its limit, detonating in a runaway fusion reaction. two fundamentally different processes, both resulting in some of the brightest events in the cosmos. Death comes in many forms, even for stars. But death is never truly the end. The material expelled by supernovas doesn't just drift away into nothingness. It goes on to create new things, new stars, new planets, new possibilities. Let's explore what happens after the explosion, in the aftermath that seeds the future. The forge of creation. There's something profound about the fact that destruction and creation are so intimately linked in the universe. Nowhere is this more true than with supernovas. These explosions, violent enough to tear apart entire stars, are also the primary means by which the universe creates the elements necessary for planets and life. To understand why, we need to think about what fusion can and cannot do. In the core of a star, lighter elements fuse into heavier ones. Hydrogen into helium, helium into carbon and oxygen, carbon into neon and magnesium, and so on up to iron. These fusion reactions release energy because the products are more stable, more tightly bound than the reactants. Energy is released in the process, and that energy is what powers the star. But iron is the end of the line for normal fusion. Iron 56 has the most tightly bound nucleus of any element. Fusing iron into heavier elements doesn't release energy. It requires energy. In normal stellar conditions, there's no reason for iron to fuse into anything heavier. The star can't power itself by making elements beyond iron. And yet, when we look at the universe around us, we find elements much heavier than iron. We find copper and zinc, silver and gold, uranium and plutonium. The entire periodic table extends far beyond iron. Where did all those heavier elements come from? The answer, for most of them, is supernovas. The extreme conditions in a supernova explosion provide exactly what's needed to create elements beyond iron. When the shock wave from the collapsing core plows through the outer layers of the star, it heats the material to billions of degrees. Neutrons, produced in abundance during the core collapse, flood through this hot material. These neutrons can be captured by nuclei, adding to their mass. With enough neutron captures, a nucleus can become unstable, undergoing beta decay, where a neutron transforms into a proton, increasing the atomic number by 1 and creating a new element. There are actually two main processes for building heavy elements through neutron capture, called the S process and the R process. The S process, or slow process, happens in normal stellar conditions, where neutrons are captured slowly relative to beta decay timescales. But the R process, or rapid process, requires an intense flux of neutrons, where captures happen faster than beta decay. This drives nuclei far from stability, creating very neutron-rich isotopes that then decay back toward stability, leaving behind heavy elements. Core collapse supernovas were long thought to be the primary site for the R process, though recent research suggests that neutron star mergers might be equally or more important for producing the heaviest elements. But there's no doubt that supernovas produce significant amounts of heavy elements through various mechanisms. The elements created in the star's core during its life, all that carbon and oxygen and silicon and iron, are also expelled into space by the supernova. In fact, without the explosion, those elements would be trapped inside the neutron star or black hole remnant, effectively removed from the universe. The supernova is what liberates them, what returns them to the interstellar medium where they can be incorporated into future generations of stars and planets. Think about what this means. The oxygen you're breathing right now was created in the core of a massive star that lived and died billions of years ago. The carbon in your DNA, the calcium in your bones, the iron in your hemoglobin, all of it came from stars that exploded as supernovas before our sun even existed. Carl Sagan famously said, "We are made of star stuff." And he was absolutely right. But it's more specific than that. We are made of supernova stuff. We are the products of stellar explosions that happened before our solar system formed. When a supernova explodes, it ejects several solar masses of material into space at tremendous velocities. This debris, enriched with heavy elements, plows into the surrounding interstellar medium, creating an expanding shell of hot gas. The kinetic energy of the explosion heats the interstellar medium, and the shock wave compresses nearby gas clouds. This compression is crucial because it can trigger the formation of new stars. Normally, interstellar gas clouds are supported against gravitational collapse by a combination of thermal pressure and magnetic fields. But when a supernova shockwave passes through a cloud, it compresses the gas, increasing its density. If the compression is strong enough, parts of the cloud can become gravitationally unstable, collapsing under their own weight to form new stars. In this way, supernovas are not just recycling centers, taking old stars and breaking them down into raw materials. They're also nurseries, actively triggering the birth of new stars. There's evidence that our own solar system was born in a region influenced by a supernova. Some meteorites contain tiny grains of material with isotopic ratios that could only have come from a supernova, and these grains appear to be older than the solar system itself, suggesting they were part of the raw material that collapsed to form the sun and planets. So the supernova that contributed to our solar system's formation not only provided the heavy elements necessary for rocky planets like Earth, but also may have provided the push that triggered the gas cloud to collapse and form the sun in the first place. Without that supernova or supernovas like it, we wouldn't exist. The Earth wouldn't exist. The sun wouldn't exist. Every breath you take, every time you feel the calcium of your bones supporting you, every beat of your heart powered by iron-based hemoglobin, you're benefiting from the violent death of stars that exploded billions of years before you were born. It's a humbling thought and a beautiful one. Your very atoms have journeys that span cosmic time and space. The enrichment of galaxies with heavy elements is an ongoing process. When the first stars formed in the early universe, shortly after the Big Bang, they were made almost entirely of hydrogen and helium, the only elements produced in significant quantities in the Big Bang itself. Those first stars, sometimes called population 3 stars, lived and died without planets because there were no heavy elements to form rocky worlds. But when those first stars exploded as supernovas, they seeded their environments with the first heavy elements. The next generation of stars formed from gas that was slightly enriched with carbon and oxygen and silicon. Those stars, in turn, lived and died, creating more heavy elements. With each generation, each cycle of birth and death, the universe became progressively richer in heavy elements. Astronomers call elements heavier than helium metals, even though that includes elements like carbon and oxygen that we don't usually think of as metallic. The metallicity of a star or galaxy is a measure of how many generations of star formation have occurred. Old stars have low metallicity because they formed from relatively pristine gas. Young stars have higher metallicity because they formed from gas that had been enriched by many previous generations of stars. Our Sun has a metallicity that places it roughly in the middle of the range for stars in our galaxy. About 1.4% of the Sun's mass is elements heavier than helium. That might not sound like much, but it's enough to make a profound difference. Without those heavy elements, without the supernova contributions from billions of years of stellar evolution, we wouldn't have rocky planets, liquid water, or complex chemistry. We wouldn't have life. Take a deep breath and let this sink in. You are a temporary arrangement of atoms that were forged in stellar furnaces and dispersed by cosmic explosions. In a very real sense, you are the universe contemplating itself, made possible by cycles of creation and destruction that have been repeating for billions of years. But supernovas don't just create and disperse elements. They also leave behind structures, remnants that glow for thousands of years, visible reminders of the explosion. Let's explore what remains after a star has died. The aftermath, supernova remnants. When a star explodes as a supernova, the show doesn't end with the initial flash of light. The expanding debris continues to interact with the surrounding interstellar medium for thousands of years, creating structures called supernova remnants that can be spectacularly beautiful and scientifically fascinating. Imagine the scene. The supernova has faded from view, its peak brightness a memory. But the debris is still expanding outward at thousands of kilometers per second. As this hot, fast-moving gas collides with the surrounding interstellar medium, the slower, cooler gas that fills the space between stars, it creates a shock wave. The shock heats the gas on both sides to millions of degrees, causing it to emit X-rays, visible light, and radio waves. Over centuries and millennia, the expanding shell of debris sweeps up more and more of the surrounding gas, creating a growing bubble of hot material. From Earth, we see this as a glowing shell, often roughly spherical but sometimes irregular, depending on the structure of the surrounding medium and the details of the explosion. There are several types of supernova remnants, classified by their appearance and the physical processes that power them. Shell-type remnants look like hollow spheres, bright at the edges where we're looking through more of the hot shell, and dimmer in the center. This is called limb brightening. The expanding shell is where the supernova ejector meets the interstellar medium, and the shock wave heats the gas, causing it to glow. Then there are what astronomers call crab-like remnants, or plerions, named after the most famous example. These look more like filled blobs than hollow shells, and they're powered by a pulsar at the center. Let me tell you about the Crab Nebula because it's one of the most remarkable objects in the sky and a perfect example of a supernova remnant. On July 4th, 1054, Chinese astronomers recorded a guest star in the constellation we now call Taurus. This new star was bright enough to be visible during the daytime for about 3 weeks and remained visible to the naked eye at night for almost 2 years. The event was also recorded by Japanese observers and possibly by Native American peoples, with a pictograph in New Mexico that might depict the supernova. What those observers witnessed was a supernova exploding just 6,500 light-years away. The exact nature of the star that died remains uncertain, though astronomers believe it was likely a massive star with a mass somewhere between 8 and 12 times the Sun's mass. When it exploded, it left behind a nebula that we now call the Crab Nebula, one of the most studied objects in all of astronomy. The Crab Nebula spans about 11 light-years across now, still expanding from the explosion nearly 1,000 years ago. But what makes it truly special is what's at its center. A pulsar, a rapidly rotating neutron star that spins 30 times per second, emitting beams of radiation like a cosmic lighthouse. This pulsar, called the Crab pulsar, was discovered in 1968 and was one of the first pulsars ever found. Its discovery was crucial because it proved that pulsars are rotating neutron stars, not pulsating white dwarfs as some had thought. The pulsar is incredibly energetic, pouring about 10 to the 38th watts of power into its surroundings, roughly 100,000 times the total energy output of our Sun. This energy from the pulsar powers the nebula's glow. The pulsar creates a wind of high-energy particles, mostly electrons and positrons, moving at nearly the speed of light. These particles interact with magnetic fields in the nebula, producing synchrotron radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The Crab Nebula is one of the brightest sources in the sky at nearly every wavelength. Recent observations with the James Webb Space Telescope have revealed new details about the Crab Nebula's composition and structure. The infrared observations show the distribution of dust within the nebula, material created in the supernova explosion or by the pulsar's wind. These observations are helping astronomers determine what type of star exploded to create the crab and exactly what kind of explosion it was. Some recent research suggests it might have been an electron capture supernova, a rare type that occurs in stars with masses at the low end of the range that can produce supernovas, though this interpretation remains under investigation. The Crab Nebula is expanding at about 1,100 kilometers per second. At that rate, you can actually measure the expansion by comparing images taken years apart. This expansion confirms that the nebula is indeed the remnant of the 1054 supernova, and it allows astronomers to study how supernova remnants evolve. But the Crab is just one example. There are many other famous supernova remnants, each with its own story. Cassiopeia A, the brightest radio source in the sky outside the solar system, is the remnant of a supernova that exploded around 1680, though it was apparently not observed at the time due to obscuring dust. Cassiopeia A is about 10 light-years across and is still expanding rapidly. It's a rich source of information about supernova nucleosynthesis because different parts of the remnant show different elements, revealing the layered structure of the progenitor star. The remnants of Tycho's supernova of 1572 and Kepler's supernova of 1604, both Type 1a thermonuclear supernovas, are also well studied. These are primarily shell-type remnants, expanding spheres of hot gas visible in X-rays and radio waves. Unlike the Crab, no central pulsar has been detected in these remnants, which makes sense because Type 1a supernovas completely destroy the progenitor star, leaving no remnant behind. As supernova remnants age, they gradually slow down as they sweep up more and more of the surrounding interstellar medium. After tens of thousands of years, a remnant will have expanded to perhaps 100 light-years across, moving at perhaps 100 kilometers per second or slower. Eventually, after perhaps 100,000 years, the remnant merges with the general interstellar medium, its identity lost, but its contribution of heavy elements absorbed into the galaxy's ecology. The impact of supernova remnants on the galaxy is profound. They heat the interstellar medium, creating a temperature structure where some regions are much hotter than others. This temperature variation drives dynamics in the galaxy, creating what's sometimes called the galactic fountain, where hot gas rises out of the galactic disk. cools, and falls back down. Supernova remnants are also thought to be the primary sources of cosmic rays, high-energy particles, mostly protons, that zoom through space at nearly the speed of light. As the shock waves from supernova remnants plow through the interstellar medium, they can accelerate particles to extremely high energies through a process called Fermi acceleration. These cosmic rays fill the galaxy, and some of them eventually reach Earth, constantly bombarding our atmosphere. The beauty of supernova remnants isn't just scientific. Images from telescopes like Hubble and Chandra show these objects in stunning detail. Intricate filaments of glowing gas, shells of multicolored light, pulsar-wind nebulae with jet-like structures. They're reminders that the universe is not just violent, but also artistic, creating beauty from destruction. Let yourself imagine floating in space near a supernova remnant, watching the glowing filaments slowly expand, feeling the warmth of the X-rays and radio waves, seeing the colors shift as different elements glow at different wavelengths. It's a cathedral of physics, a monument to a star that once lived and is now gone, but whose legacy continues to shape the galaxy. These remnants are the visible scars of stellar deaths, lasting for millennia before finally fading into the background. They're proof that even in death, stars continue to influence their environments to contribute to the ongoing story of the galaxy. But all of this makes us wonder, when will the next supernova happen in our galaxy? When will we have the chance to witness one of these spectacular events with our own eyes? Let's turn our attention to the search for the next visible supernova. Watching for the next great show. The last supernova visible to the naked eye in our galaxy was observed in 1604. Johannes Kepler, the famous astronomer, studied it extensively, and it's now known as Kepler's supernova. Before that, there was Tycho's supernova in 1572, observed by Tycho Brahe. And going back further, there's the famous supernova of 1054 that created the Crab Nebula, plus a handful of others recorded by ancient astronomers. So it's been more than 400 years since anyone on Earth has seen a supernova in our own galaxy with the naked eye. And that's a long time too long, really, because statistically, we should be overdue. Based on the number of supernova remnants we can see in the Milky Way and estimates of how long remnants remain visible, astronomers calculate that our galaxy should produce about 2 to 3 supernovas per century on average. That means we're missing out. Most supernovas in our galaxy are hidden from view by intervening dust and gas. The Milky Way is a spiral galaxy, and we're located in the galactic disk, where there's a lot of obscuring material. A supernova on the far side of the galaxy, or even one relatively close, but behind dense molecular clouds, might be completely invisible to optical telescopes. But every now and then, we get lucky. A nearby supernova, one within a few thousand light years and with a clear line of sight to Earth, produces a spectacular show. And astronomers around the world are watching, waiting for the next one. The star everyone's talking about right now is Betelgeuse. Betelgeuse is the bright red star marking the shoulder of Orion the Hunter, one of the most recognizable constellations in the night sky. It's normally the 10th brightest star visible to the naked eye, though it varies in brightness. And Betelgeuse is a red supergiant, exactly the kind of star that should eventually explode as a core collapse supernova. The star is massive, somewhere between 15 and 20 times the mass of the Sun, though estimates vary. It's also enormous, so bloated that if you placed it at the center of our solar system, its surface would extend beyond the orbit of Mars, possibly as far as Jupiter's orbit, and it's relatively close, at least in astronomical terms, about 600 to 700 light-years away. Most importantly, Betelgeuse is old for a massive star. It's been around for about 8 to 10 million years, and it's exhausted the hydrogen in its core, the helium in its core, and is now in the late stages of burning heavier elements. It's a dying star, and everyone knows it. The question is, when will it die? The honest answer is, nobody knows. It could be today. It could be 100,000 years from now. The challenge is that we can't see inside the star to know exactly which fusion stage it's in or how much fuel remains. For years, astronomers have said Betelgeuse will explode sometime in the next 100,000 years, which is basically a way of saying, we have no idea. But some recent events have made people wonder if it might be sooner rather than later. In late 2019 and early 2020, Betelgeuse underwent what astronomers called the Great Dimming. Its brightness dropped by about 2.5 magnitudes, making it only about 40% as bright as usual. For a while, it wasn't even in the top 20 brightest stars in the sky. People wondered, is this it? Is Betelgeuse about to explode? As it turned out, no. The dimming was caused by the star ejecting a huge plume of material that cooled to form dust, temporarily blocking some of the star's light from our view. By mid-2020, Betelgeuse had returned to its normal brightness. But the event was a reminder of how variable and unpredictable red supergiants can be in their final stages. Then, in 2023, Betelgeuse brightened significantly, becoming one of the 7 brightest stars in the sky. Again, people wondered if something dramatic was happening, and again it seems to have been normal variability, possibly related to the after-effects of the 2019 to 2020 ejection event. A paper published in 2023 suggested that Betelgeuse might be in the late stages of carbon burning, the final fusion stage before core collapse. If that's true, the star could explode in tens of years rather than thousands or tens of thousands. But other astronomers have disputed this, arguing that the star might still be in helium burning with a longer timescale remaining. The truth is, we don't know. Predicting when a specific star will go supernova is one of the hardest problems in astrophysics. Stars don't send out warnings, they just explode. But whenever Betelgeuse does explode, it will be spectacular. Simulations suggest that Betelgeuse as a supernova will reach an apparent magnitude of about -10 to -12. To put that in perspective, the full moon is magnitude -12.7. So Betelgeuse will be almost as bright as the full moon, perhaps about half as bright, but concentrated into a single point of light. It will be visible during the day, a bright star in broad daylight. At night, it will be bright enough to cast shadows. You'll be able to read by the light of the Betelgeuse supernova. It will be the most dramatic astronomical event in recorded history, visible to every person on Earth for weeks or months. And here's the wonderful thing. It won't hurt us. Betelgeuse is far enough away, about 600 to 700 light-years, that the radiation from the supernova poses no danger to Earth. Calculations suggest that a supernova would need to be within about 160 light-years to pose a threat to life on Earth. Betelgeuse is 4 times that distance. We'll get the show without the danger. We'll get to witness a cosmic spectacle that hasn't occurred in 400 years, a supernova bright enough to rival the moon. in one of the most recognizable constellations in the sky. Astronomers have set up an early warning system called the Supernova Early Warning System, or SNEWS, which uses an array of neutrino detectors around the world. When a core collapse supernova happens, the neutrino burst from the collapsing core reaches Earth before the light does, because the neutrinos escape from the core immediately, while the light has to fight its way through the outer layers of the star. For a supernova at the distance of Betelgeuse, neutrino detectors would likely pick up the signal hours or even possibly days before the optical brightening begins, giving astronomers advance notice of the impending explosion. This advance warning would give astronomers time to point every available telescope at Betelgeuse to catch the shock breakout, the initial flash when the shock wave breaks through the stellar surface. That's never been observed for a galactic supernova, and it would provide invaluable data about the explosion mechanism. There are other candidates besides Betelgeuse. Antares, another red supergiant, is also relatively nearby at about 500 light-years. Rigel, the bright blue supergiant in Orion, will eventually explode, though it's probably not as close to the end as Betelgeuse. Eta Carinae, a massive and unstable star in the southern hemisphere, has been ejecting material for decades and might explode at any time, though it's hidden behind dust that would dim the visible light significantly. The point is, the next galactic supernova could happen at any time. It could happen tomorrow. It could happen while you're reading this, though we wouldn't know for hundreds of years because the light hasn't reached us yet, or it could happen centuries from now. The universe works on its own schedule, not ours. But the waiting is part of the beauty, the anticipation, the knowledge that somewhere, out there, a star is dying right now, collapsing, exploding, and in the years or decades or centuries to come, its light will reach Earth, and we'll look up and see a new star in the sky, a brilliant beacon announcing death and rebirth. Let yourself feel the patience of cosmic time. 400 years is a long time for humans, but it's nothing to the universe. The stars will explode when they're ready, and when they do, we'll be watching. In the meantime, every clear night, you can look up at Betelgeuse in Orion's shoulder and think, is tonight the night? Is this the last time I'll see Betelgeuse as a red supergiant before it transforms into a brilliant supernova? Probably not, but maybe. And that maybe is enough to make the stars feel alive, dynamic, filled with potential. The universe is waiting. The stars are burning. And someday, soon on cosmic scales, one of them will explode, and we'll be there to see it. The beauty in destruction. Take a breath now and let yourself settle into this final thought. Supernovas are not just explosions. They're transformations. They're the universe's way of recycling, of taking the old and making it new, of ensuring that nothing is ever truly lost, only changed. When you look at a supernova, you're witnessing the most violent event in nature alongside one of the most creative. You're seeing destruction and birth in the same moment the star dies, yes, but its death scatters the elements that will form the next generation of stars and planets. The explosion ends one story and begins countless others. There's a poetry to this that transcends the physics. In a universe governed by entropy, where everything tends toward disorder and decay, supernovas represent something different. They're moments of violent reorganization, where concentrated stellar matter is dispersed into space, enriching the universe, making possible worlds that couldn't have existed before. Your body contains atoms from multiple supernovas. Some of the iron in your blood might have come from one star that exploded 5 billion years ago. Some of the calcium in your bones might have come from a different star that exploded 6 billion years ago. You are a mosaic of stellar deaths, a living testament to the creative power of destruction. The cycle continues endlessly. Stars form from clouds of gas and dust. They live, fusing hydrogen into helium and building heavier elements in their cores. When they die, they return those elements to space. New clouds, enriched with those elements, collapse to form new stars. Those stars live and die in turn. With each cycle, the universe becomes richer in heavy elements, more capable of forming complex structures, more capable of producing planets, water, life. We don't know if life exists elsewhere in the universe, but we know that wherever it does exist, it depends on supernovas. Life requires heavy elements, carbon for organic chemistry, nitrogen for proteins and DNA, oxygen for water and respiration, phosphorus for DNA and ATP, sulfur for amino acids, iron for hemoglobin and enzymes. All of these elements in sufficient quantities require supernovas. So when we study supernovas, we're studying our own origins. We're asking, where did we come from? What processes in the universe made our existence possible? And the answer, in part, is the death of stars. Not a gentle death, not a quiet fading, but a violent explosion that shakes the cosmos and seeds the future. There's comfort in this, if you look at it the right way. Nothing is wasted. The star doesn't die and vanish. It lives on in its descendants, in the new stars and planets formed from its remains. Its atoms persist, transformed but not destroyed, continuing the story in new forms. In some distant future, billions of years from now, our own sun will die. Not as a supernova, our sun isn't massive enough for that, but as a planetary nebula, puffing off its outer layers and leaving behind a white dwarf. Those outer layers will mix with the interstellar medium, carrying the helium and carbon produced in the sun's core. And perhaps, in the far future, some of those atoms will become part of new worlds, new stories. The cycle continues, always. Astronomers spend their careers studying supernovas because these events are keys to understanding the universe. They tell us about stellar evolution, about the creation of elements, about the expansion of the universe, about the nature of matter under extreme conditions. Every supernova we observe adds to our knowledge, fills in pieces of the cosmic puzzle. But beyond the science, there's something deeply human about our fascination with supernovas. They remind us that we live in a dynamic universe, a universe where things change, where the old makes way for the new, where destruction and creation are two sides of the same coin. When you look up at the night sky, you're seeing stars at different stages of their lives. Some are young, just beginning their journey. Some are middle-aged, like our sun, steadily burning hydrogen. Some are old, approaching their end. And somewhere unseen, some are dying right now, exploding as supernovas, though their light won't reach us for thousands of years. The universe is filled with these ongoing stories. Billions of stars living out their lives, each one a tiny universe unto itself, each one connected to all the others through the web of cosmic evolution. Let yourself feel small before this immensity. Let yourself feel the weight of time, the span of space, the scale of energy. And then let yourself feel connected, because you're not separate from this. You're part of it. Your atoms came from stars. Your existence depends on supernovas that happened before the Earth even existed. You are the universe, temporarily arranged in a form that can think and wonder and ask questions. You are made of the same material as the stars, subject to the same physical laws, part of the same cosmic story. And when you sleep tonight, your atoms will still be here, vibrating with thermal energy, interacting with the atoms around you, participating in the endless dance of matter and energy that makes up reality. Those atoms have been on journeys you can barely imagine through the cores of stars, across interstellar space, through the formation of the solar system, through the evolution of life on Earth, and now, temporarily, they're you. Tomorrow you'll wake up and the atoms will still be you, mostly. A few will have been exhaled or shed or excreted, beginning their next journey. And someday, billions of years from now, long after you're gone, those atoms will continue, perhaps becoming part of new worlds under new suns, carrying forward the legacy of the supernovas that made them. This is the great cycle. This is the cosmic story. Birth, life, death, rebirth. Endlessly repeating, endlessly creating, endlessly transforming. Supernovas are not endings, they're transitions. They're the universe's way of ensuring that nothing is ever truly lost, that every star that dies contributes to the stars that will be born, that the story continues forever. Rest now in this knowledge. Let it settle into your thoughts as you drift towards sleep. The universe is ancient and vast and filled with wonders. Supernovas are among the greatest of those wonders, spectacular deaths that are also the seeds of future life. Somewhere tonight, a star is collapsing. Its core is imploding, reaching nuclear densities, bouncing, sending a shockwave outward. In a few hours or days, that star will brighten dramatically, becoming visible from across the cosmos. And perhaps centuries or millennia from now, someone will look up and see that light, that ancient explosion finally reaching them, and they'll wonder at the beauty and violence of the universe. The cycle continues. The stars die and are born. The elements are created and dispersed and gathered again. And through it all, the universe evolves, growing more complex, more rich, more capable of producing wonders. You are one of those wonders. Never forget that. As we come to the end of our journey through the deaths of stars, I want to leave you with one final image. Picture yourself standing under a clear night sky, far from city lights. The Milky Way stretches overhead, a river of stars crossing the heavens. Each point of light is a star, each star a nuclear furnace, each furnace burning through its fuel at its own pace, moving inexorably toward its eventual end. Some of those stars will die quietly, fading into white dwarfs and slowly cooling over trillions of years. But some, the massive ones, the spectacular ones, will die as supernovas, and when they do, they'll briefly outshine everything else, a final blaze of glory before the transformation. You can't predict which stars will explode or when, but you know it's coming. Somewhere among those billions of points of light, stars are approaching their end. Maybe tonight, maybe tomorrow, maybe centuries from now. But it's coming, and when it happens, when the next galactic supernova appears in our sky, it will be a gift. A chance to witness something that hasn't been seen in over 400 years. A moment of cosmic significance, a reminder that we live in a universe where stars die and are born, where matter transforms and persists, where the old becomes new. Until that moment arrives, we wait. We watch. We study the stars we have, learning their secrets, preparing for the next supernova, anticipating the show. And in the meantime, we remember, We are made of stardust. We are the universe's way of knowing itself, and we are connected through our atoms to every star that has ever lived and died. If you enjoyed learning about supernovas, the universe's most beautiful deaths, please consider liking this video and subscribing to the channel. There's so much more to explore in the cosmos, so many more wonders to discover. And I'll be here, guiding you through them, one video at a time. Thank you for joining me on this journey. Sleep well, and may your dreams be filled with stars. Sweet dreams and clear skies.